Hello, I'm Seema and welcome to part 10 of the chapter States of Matter. In the previous video, I told you about the Gay-Lussac's law. According to this law, as the temperature of an enclosed gas increases, the pressure also increases if the volume is constant. If a gas is enclosed, it means the number of moles are fixed. And if it's enclosed in a vessel, that is, it's in a sealed vessel, it means that the volume is also fixed, considering that the vessel is not expandable like a balloon. So whatever this container is, if it is enclosed in a container of fixed volume, if you increase the temperature, the pressure also increases. So the relation we arrived at was P1 upon T1 is equal to P2 upon T2. Using this relation, we are now going to solve three numerical problems that I have chosen from the New York Prentice Hall textbook, the chemistry textbook. Let us come straight to the problems. The first question is that the gas in a used aerosol can is at a pressure of 103 kilopascals at 25 degrees Celsius. If the can is thrown into a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? I told you that whenever we use these equations, that is P1 upon T1 in the gas laws, whenever we use temperature in the gas laws, the temperature should be in Kelvin. That is, it should be the absolute temperature. In Charles' law, I explained why do we choose the Kelvin scale, and then since we have a combined gas law too, therefore we choose to have the same unit in all the gas laws. So the temperature, whenever we are solving numerical problems which are of this kind, that is, which are of Gay-Lussac's law, if the temperature is given to us in Celsius, we are first supposed to convert that into the Kelvin scale and then use the formula. Now for the formula, there are four variables, that is P1, T1, P2 and T2, three out of which would be known to us and the fourth has to be calculated. So let us see in this problem what are the three variables that are known to us and which is the fourth one that has to be calculated. The variables that we need are P1, T1, P2 and T2. Okay, these are the four variables we are looking for. The gas in a used aerosol can is at a pressure of 103 kilopascals. It means P1 is 103 kilopascals, right? And a temperature of 25 degrees Celsius. We have the temperature in Celsius, we'll have to convert it to Kelvin. If the can is thrown into a fire, what will be the pressure when the temperature reaches 928 degrees Celsius? It means both the temperatures have to be converted to Kelvin scale and it is P2 that we are looking for. Before we come to the formula, let us first convert the units. In order to convert degrees Celsius to Kelvin, we need to add 273 to whatever the temperature is in the Celsius scale. So add 273 to 225, 273, 5, 6, 7, 8, 7, 8, 9, 298 Kelvin would be T1 and T2 would be equal to, add 273 to this, 8, 9, 10, 11, 10, 12. 1201 Kelvin, right? So these are the temperatures T1 and T2 in Kelvin scale. Now we have to find out P2. So the relation that we have is P1 upon T1 is equal to P2 upon T2. In order to get P2, what will we do? To have only P2 on this side, we'll say P2 would be equal to P1 upon T1 into T2 because T2 will go here only to have P2. So P2 would be equal to P1 upon T1 into T2. From this relation, we'll get P2. Let us substitute the values. P1 is 103 kilopascals. T2 is 1201 Kelvin. T1 is 298 Kelvin, right? The Kelvin and the Kelvin, they will get cancelled. You should get your answer in kilopascals. So when you plug these values in the calculator, the value that you get is 415 kilopascals. 415 kilopascals. Or you could say, in scientific notation, this would be written as 4.15 into 10 to the power 2 kilopascals. In scientific notation, we have only one digit before the decimal, the rest are put after the decimal, and it's shown as an exponent of 10, the value. So 415 kilopascals is P2, or 4.15 into 10 to the power 2 is our answer. Let us move on to the second numerical problem. A sample of nitrogen gas has a pressure of 6.58 kilopascals. At 539 Kelvin, the temperature given to us is already in Kelvin, so conversions would not be required. If the volume does not change, volume is fixed. Remember, when you get these problems during your examination, you would not know which gas law to use. So therefore, at that time, you will have to pay attention to what are the values given to you, whether P1, T1, V1, V2, P1, V1, T1, or P2, V2, T2, and N1 and N2. Which out of these are given, and which two are fixed, and what is the relation of the other two? And if you're using the combined gas law, then what are you supposed to do? We'll come to that in a later video. So right now, let us solve this. What are the variables given to us? A sample of nitrogen gas has a pressure of 6.58 kilopascal. So P1 is 6.58 kilopascal. What is T1? T1 is 539 Kelvin. What is P2? If the volume does not change, what will be the pressure? It means P2 is asked from us at 211 Kelvin. 211 Kelvin is T2. Now, we are asked P2. So solving using this relation again, P2 is equal to P1 upon T1 into T2, substituting the values. P1 is 6.58 kilopascal into T2 is 211 Kelvin upon T1 is 539 Kelvin. Cancel out the Kelvin. Your answer should be in kilopascals. Remember, whenever you cancel out the units first, you must always notice that the units that you are left with should be the unit for that quantity that you're looking for. If it's pressure, it's kilopascals, it means you've plugged in the values at the right places, because the other unit should cancel out, and in the result you should get the unit you are looking for. So when you solve this, the answer you get will be 2.58 kilopascals. 2.58 kilopascals would be your answer, right? I'll now solve one more numerical problem, and let me just write it down for you and come back in a minute. Okay, so now we have the third problem. The problem is that the pressure in a car tire is 198 kilopascals at 27 degrees Celsius. Again, the temperature is in Celsius, so we'll have to convert it to Kelvin. After a long drive, the pressure is 225 kilopascals, that is, the pressure has gone up. And we know, according to Gay-Lussac's law, if temperature goes up, pressure goes up. So since the pressure has gone up, the temperature should also go up. Whenever you find the answer to your numerical problem, you should also pay attention to this, that has the pressure, whatever the variable was, has it gone up, then the other one should also go up according to Gay-Lussac's law. I'll come to that at the end of this result now. What is, after a long drive, the pressure is 225 kilopascals, which means that is P2. What is the temperature of air in the tire? It means now you've been asked T2. You have to assume that volume is constant. During your exam, it is this which will be your hint for using Gay-Lussac's law. Volume is constant, the number of the gas is trapped inside a tire, so the number of moles is also fixed. Number of moles and volume are fixed, so it's a relationship between pressure and temperature. The relationship between pressure and temperature is Gay-Lussac's law, and they have a direct relationship. The relation you use is P1 upon T1 should be equal to P2 upon T2. So the four variables that we are looking for, let us start looking for them again and begin our solution. We are looking for P1, we are looking for T1, we are looking for P2, and we are looking for T2, right? P1, a tire is at 198 kilopascal is the pressure, P1. The temperature is 27 degrees Celsius. Remember, Celsius will have to be converted to Kelvin. And the final pressure is 225 kilopascals, and it is T2 that we are looking for. So let us first convert this into the Kelvin scale. So T1 would be add 273 to any Kelvin, to any degree Celsius, you'll get the answer in Kelvin. So T1 would be, this is 0, 8, 9, 10, it is 300 Kelvin. So T1 is 300 Kelvin, while T2 is to be found out. So now let us use the relation P1 upon T1 is equal to P2 upon T2. Now T2 is in the denominator and we want it to come up here. So what should we do in order to get T2 in the numerator, and we are looking only for T2, so it should be on one side of the equation and all the other three variables should go to the other side. In order to do that, we can either just flip numerator to denominator, or I can take T2 here and bring P1 here and take T1 there. Or as it is explained in the US, you would, whatever you have to take to the other side, you multiply on both sides with that quantity in order to cancel it out and change its sign. For example, I want to take T2 here, so I will multiply both sides by T2. So I'll write P1 upon T1 is equal to P2 upon T2. So if I multiply both sides by T2, the T2 on this side gets cancelled, I get T2 here. Now, I want P1 to go here. So what should I do? I should divide both sides by P1. Now, if I divide both sides by P1, the P1 will get cancelled here and I get it on this side. Now I'm left with T1, which I want it to go to this side. So what am I left with now? Let me first bring it here not to create too much confusion. We are left with T2 upon T1 is equal to P2 upon P1. But I'm looking for T2 and I want T1 to go here. So I'll multiply both sides by T1 now. And the T1 also goes to this side. And in India, students are quite used to just moving it without these steps. We just shift it. So now you're looking for T2, the equation we get is T2 is equal to P2 upon P1 into T1. So let us plug in these values. We'll get T2 would be equal to, P2 is 225 kilopascals into T1 is 300 Kelvin upon P1 is, here, P1 is 198 kilopascals. Now, the kilopascal and kilopascal will get cancelled and we get our answer in Kelvin. So, we are looking for temperature and we are getting the answer in Kelvin, which means that we have plugged in the values at the right places. So, T2 should be in Kelvin. When you plug in these values, you will get 340.9 Kelvin. That is, T2 is 340.9 Kelvin. So with this, we come to an end to the topic Gay-Lussac's law. In the next video, we'll do the Avogadro's law. If you found this video helpful, please give it a thumbs up. I'd appreciate that. Please subscribe to my channel, share the videos with your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.